Hi everyone, thanks for joining us for Coding Practice with Kickstart. My name is Lizzie and I am the Kickstart Program Manager. We hope you enjoyed practicing our problems during the session and learned something new to kickstart your coding competition journey. Throughout this video, we'll hear from various Google engineers on how you can go about solving each of the problems you just attempted. Regardless of what you solved, we hope these walkthroughs will provide some helpful tips and tricks to use for future competitions. If you're watching this video live, feel free to ask any questions to our Google moderators in the chat feature below. Now let's hear from some of my colleagues who will walk you through the problems from this week's session. Take it away.
Hi everyone, welcome. My name is Federico and I'm a software engineer in Google Play Analytics. I'm here to talk about the problem Sherlock and the Parenthesis. The problem is a good example of what you can expect from an easy problem from Google Kickstart. The first thing you need to understand is the problem statement. Let's go through it carefully. The problem is about a maximum number of balanced strings. For this, we should focus on what a balanced string is. According to the problem statement, a string is balanced if it matches one of the following conditions. A is an empty string, B is of the form open parens, S close parens, where S is a balanced string, or C it has the form S1, S2, where S1 is a balanced string and S2 is a balanced string as well. Maybe let's try a naive solution for this one. Let's explore this idea. Maybe we can generate all the permutations with a given number of left and right parentheses. For this, there are helper methods in all programming languages. There will always be some complexity cost for generating these permutations, which will be in the order of the possible permutations. And for counting the number of balanced substrings, we could just start anywhere in the string and start counting how many balanced parentheses there are. Then try starting on the next position and do the same. This will take at least on squared. The total time will be on squared times the time to generate the permutations. Let's continue reading. You can see test case. Okay, that's normal. And we want to have the maximum number of balanced non-empty substrings. Should we just go ahead and implement our naive solution? Let's look at the limits. The large test case says there could be up to 10 to the 5 parentheses. Even optimizing the naive solution, it won't work with this kind of limits. It's always important to check the limits. I actually think of them as hints for the type of solution that is expected. So our naive solution is too expensive. But what about just calculating the number of balanced strings directly? Yeah, I wonder if there's a closed form solution for this problem. At this point, I recommend grabbing a pen and a paper and writing down some examples. What is the better arrangement of parentheses? Let's take the case, for example, of L equals 3 and R equals 2. It is always good to come up with your own examples and try to figure out how to solve them. I do this even before reading the provided examples. Take a look at the slide. We can have the first arrangement where we have only one balanced substring. Or we can have a much better arrangement like the second one. I think we can imagine this is the best we can do. Can you prove this is optimal? So, how many pairs of parents there are? You might learn at school about the handshake problem. I like to think about this one as, imagine there's a room and there are n people coming in one by one. Each person is coming in and giving a handshake to everyone in the room. The second person will have to shake one hand. The last person will have to shake n minus 1 hands. So the total number of handshakes is 1 plus 2 plus n minus 1 hands, which evaluates to n times n plus 1 over 2. So what is n in our case? We want the balanced strings to be of the form open parens, close parens. So basically, we need to ensure each left parens has a right parens. So we are constrained by the lesser of these two. So basically, n is the minimum of L and R. We now have everything to start coding. Let's do it. Let's just do what we did before. Here we have some boilerplate code to read from input and some boilerplate code to write from the output. I like to write boilerplate code first and then code the solution. Let's just put our solution together. This code is in very simple Java language. Okay, one final thought. What is the time complexity of our solution? If you're thinking very fast, that is correct. We say the time complexity of the solution is O of 1, which means it's constant with respect to the input. Also, the space complexity should be constant. Now we can submit and it should work. Okay, so to recap. It is okay to explore possible solutions. Take a look at the limits. They provide hints on the type of solutions expected. Make up your own examples. Always have fun coding the solution. Now with problem A done, we can move forward to the rest of the problems with much more confidence. Thank you for walking through the problem with me. My colleague Kata is going to present the next problem, building palindromes.
Thanks, Federico. Hi, everyone. My name is Kata Brányiné, and I'm a software engineer at Google. I work on cloud AI and industrial solutions, and in my spare time, I started to help with coding competitions. We hope you enjoyed trying out all the problems from the practice session. Today, I'm going to walk you through the problem building palindromes. Let's jump in. In this problem, given a string, we have to count how many of its substrings defined by the input intervals can be rearranged to form a palindrome. A palindrome is a word which is the same as its reversed version. You could notice that the naive approach, rearranging a substring in all possible permutations and checking that palindrome feature, wouldn't fit in even for shorter intervals, as for example 15 letters would build up 15 factorial strings, and this number is way more than 10 to the power 10. But let me highlight that you don't need to create any palindrome. You only need to decide whether it is possible to rearrange the letters of the substring so that it yields a palindrome, or it's not possible. Based on the feature of the palindrome, you can conclude the following observations. Letters of an even-length palindrome can be paired entirely. Letters of an odd-length palindrome can be paired except exactly one character, the middle one. The strings that are rearrangeable to palindrome are actually rearranged palindromes, so they also have the mentioned feature. Now we reduce the problem to count all the character occurrences for the substring, and if there is at most one of them having an odd sum, the substring counts to the result. Worth to mention that you actually don't need to track the number of occurrences itself, only the parities. I wrote my code in Python, but you can choose any of the available programming languages. The time complexity of this solution is big O n times q, which is sufficient for the constraints for test set 1. For the test set 2, we have a much higher number of characters as well as queries, so we have to reduce the calculations further. One approach here is to reuse the results on previously calculated intervals, and this problem is really suitable to solve using this idea with the query square root decomposition technique. I won't explain it in detail as it's still not optimal, even if it passes. Instead, let's consider some static precalculations on the input. If we know the number of occurrences of a given letter for every prefix, we get its count through any interval by the difference of the count until the last letter and the count until before the first letter. Although this precalculation needs big O n time and also big O n space in addition, the time consumption of a single query is reduced to constant. Thus, the overall time complexity sums up to big O n plus q times 26. In the code, to identify a letter, we use its index in the ABC with the help of the ORT function. During the preparation, the list seen keeps the arrays of prefix sums by letter indices, which is filled during walking through the input, while the array act holds the actual number of occurrences. After this preparation, the evaluation of an interval is done by summing up the corresponding differences modulo 2, which exactly yields the number of different letters with odd occurrences. If it is less than or equal to 1, we have found a new substring, which is a rearranged palindrome, and we count it in. That's all from me, and thanks for watching. Sarah, over to you.
Hi everyone, my name is Sarah and I'm a software engineer at Google, and I work on a team in DataWorks where we work with internal Googlers and consolidate enterprise data within Google. I'll be walking you through the problem irregular expressions. Let's start by looking at the problem statement. We're given a spell which is a string of characters and we need to determine if that spell is valid. There's a couple definitions that are given. Each valid spell will contain 3 words, which are start, middle, and end. A string of characters is considered a word if it has at least one syllable and can be 1 or more letters long. A syllable is a string of letters that includes exactly one vowel, and the vowels are A, E, I, O, and U. Note that Y is not a vowel here. So here are some examples of valid and invalid syllables. We see that if the string has 0 or more than one vowel, it's an invalid syllable. Now that we understand the problem, let's look at the constraints. First, start, middle, and end must be a word, which we defined on the previous slide as a string of letters with at least one syllable. Second, start must equal end. And lastly, start and end must have at least two syllables. There may also be random letters before and after the spell, and the string might not contain a valid spell at all. So what we're looking for is if there's some substring in the given input string that starts and ends with the same two or more syllable word, with at least one vowel between them. In the small dataset, the given string will have at most 20 characters, and for the large dataset, at most 100. Let's look at some examples. In each example, the start and end word is highlighted in green, and the middle word is highlighted in blue. In the first example, notice that the start and end word has two syllables, and the syllables themselves can be split in different ways. The second example is a string which contains extra letters at the beginning and end of the spell. The last example does not contain a valid spell in the given string. A common mistake is to think that the first FRU is a spell, but remember that the middle must contain at least one syllable, and here it contains none. Given the constraints and definitions of the problem, we can make some observations. First, we notice that the only constraint on middle is that it has one vowel. This means that there may be many random letters before or after the vowel, and it will still qualify as a valid middle word. With this in mind, we can also assume that start begins at the first vowel, and that what comes before it doesn't matter. Looking at example 1 below, where the start and end word is highlighted in green and the middle word is highlighted in blue, we can see that one valid spell is jabba majabba. However, if we assume start begins at the first vowel, we see when iterating through the string, making it abba, we see that abba maj abba would also be a valid spell, since when we look for the end word, we can push everything before the abba, in this case is just the J, to the middle word without breaking any constraints. Second, when we're looking for a valid start, once we see two vowels, we can stop and assume that the rest belongs in middle. To see this, let's look at example 2. The top two are valid spells. Let's assume that we realize that the KJ can't be part of any valid spell. Now we're looking at the A after the KJ. We iterate along, we see the second A, and now we've seen ABBA so far. We've seen the second vowel, and we can stop here. This is because we've satisfied the constraints of start already, and whatever else comes before we can just stick onto the middle word. We can safely do this because there's no constraints on the middle word, other than it must have at least one vowel. In fact, we must do this, because if we don't, we may miss potentially valid spells, as we see in the third line of this example, where we don't stop at the second vowel and miss the valid spell abba much abba. Lastly, after seeing exactly one vowel in the middle, we can begin our search for end. Again, this is because of the one constraint on middle, which is that it must have at least one vowel. Similar to tacking on any extra letters to middle word when looking for start, we do the same for end, where we search for whether end exists in the rest of the string, and if there happens to be any letters before end begins, we just assume that it belongs to middle. Looking at example 3, after we decide that the start word is ABBA, we see the next vowel A, which is highlighted in blue, and then we can look at the rest of the string, starting from ADSF onwards, and see whether ABBA appears. If it does, we say that everything before the end word ABBA is actually part of the middle. These excess letters are highlighted in yellow. Now let's go through the pseudocode. Because there may be random letters before the spell itself, we need to iterate through the spell. We first find the first and second vowels. We set the start word as a substring from the first vowel to the second vowel inclusive. We can see this in the two examples, where the start word is highlighted in green. Then we set the middle word after seeing the third vowel to be everything after start to the third vowel. This is highlighted in blue in the examples. Then we look through the rest of the string, starting from the letter right after the middle vowel. If it contains the start word, then we have a valid spell and we can return. Otherwise, we'll need to reset the start word and continue looking. In the first example, we see that start exists in the rest of the string, so we can stop. In the second example, however, we didn't find the start word, which was AE, in the rest of the string, so we'll need to reset and keep iterating. Now we reset and start looking at the first E. We set the start word to be the first two vowels we see in the string, which are now EA, which is highlighted in green. We then find the middle vowel, which is the next E. Then we look for start in the rest of the string, which we do find here, and can return. If we iterate through all the letters and don't find any valid start, then we know there is no valid spell and we can return nothing. Here's the full solution. I used Python, but you can use any programming language you are comfortable using. Notice that our code is structured a little bit differently from the pseudocode I presented earlier. For simplicity, we first find a list of all the vowels and iterate through that instead of the entire string. If there's fewer than 5 vowels, we know there cannot be a valid spell, so we can immediately return. Otherwise, we iterate through the vowels as we did in the pseudocode. Now let's look at the runtime complexity of this code. Let n be the length of the given string. We first call findAllVowels, which requires iterating through the string, which takes O of n time. After that, we have a for loop, which iterates through the list of vowels, which is also O of n in the worst case. In each iteration of the for loop, we iterate through the entire string once, when we look for the start word and check if it exists in the rest of the string after the middle vowel. Thus, the total runtime is O of n squared. I just wanted to cover one more alternate solution, which is using regex. You can use regular expressions to check whether the string conforms to the given format based on the constraints we covered earlier. Feel free to refer to the regex documentation for more details on how this works. The runtime of this is O of n, where n is the length of the string. Note that if we're constructing this for every test case, this could take up to O of c to the n construction time and space, where c is the size of the regex. Make sure to check out the full problem analysis on the problem dashboard for more details. Thanks for tuning in. Next up is Shahed, who will walk through the problem Parcels.
Hello everyone, I'm Shahed and I'm a software engineer at Google. I'm currently working in network control SRE, and when I can manage time, I try to collaborate with the coding competitions. I used to participate in Google's coding competitions during my college years. Today I'm going to discuss the problem Parcels. Let's go. Let's discuss the problem description first. You are given an n into m grid which contains either 0 or 1. 1 means there is a delivery office and 0 means the place is empty. Distance between two squares is their Manhattan distances, which means the summation of the difference between their x-axis and y-axis. For any square, the minimum distance to a delivery office is the minimum among all the distances to delivery offices. Let's call this MDTD, the minimum distance to delivery. The minimum overall delivery time for the company would be the maximum among all the MDTD. Additionally, we can build an extra delivery office anywhere we want. So, we want to build a delivery office in such a place so that the overall delivery time can be as minimum as possible. Let's check some examples. In the first example, you can see we mark the minimum distance to a delivery office for each square. If we build our new delivery office in the blue marked place, then the maximum among all these values reduces from 2 to 1. So for this given grid, the final answer will be 1. For the second example, you can see that building an extra delivery office does not reduce the maximum value. So the final answer is still 1, and we might want to skip building that extra delivery office. Let's talk about the solution, shall we? For a small test, the dimension of the grid can be at most 10, while for the larger test, it can be at most 250. For a small test, we can calculate the distance for each square for every delivery office and find the minimum among them. Now for every empty square, we can build a delivery office and can check whether it minimizes the distance to a delivery office for each square. Alternatively, we can build a delivery office in an empty square and run a unit cost shortest path algorithm called breadth first search to find the minimum distances to a delivery office for each square. For the optimal solution, we can do is that we need to find the minimum distances to delivery offices for all these squares. So the squares having the delivery office needs 0 units of time for delivery. We can treat the squares as sources and run a breadth first search algorithm. Thus, we will get all the minimum delivery time or distance for all the squares. We can build another delivery office that could reduce the maximum of these distances, right? Let's try this way. If we can check whether it's possible to build the extra delivery office in such a way that we can reduce the maximum among these distances to at least d. If we can do that for a particular d, then we can definitely do that for a d plus 1 too. So we can do a binary search to find the minimum possibility where it's possible to build the delivery office to achieve that particular answer. Let's walk through the codes. This is the breadth-first search algorithm to find the minimum distances for all squares to any source. Here we are passing the sources in a queue and calculating the MDTD, the distance from the sources for all squares. Eventually, we are returning the maximum among them, which would be the minimum overall delivery time for the company if we don't build another delivery office. And here is the binary search code to find the minimum delivery time. In the function possible, we are checking if it's possible to build another delivery office so that the minimum overall delivery time is at least mid. But how do we check if it's possible to achieve the answer for a particular D? We can write the formula for Manhattan distance in a bit different way. So, if a point is fixed, let's say the point B is fixed, then the AX plus AY, the summation of the point A's coordinates, is contributing to the answer. The maximum of the sum can contribute as the largest possible integer, and the minimum of the sum can contribute as the smallest possible integer. Either of them could contribute as the largest integer, as we are taking the absolute value here. Similar for AX minus AY, the difference between the coordinates, this is contributing similarly. Here is the code for checking if a particular D is achievable or not. In the first iteration, we are calculating the minimum and maximum value for I plus j and I minus j among all the squares whose MDTD is greater than D. In the second iteration, we are building a new delivery office in each square and checking whether it's possible to decrease the minimum overall delivery time under the given D. The time complexity for the breadth-first search is order of n into m. If the initial grid contains a single delivery office, then the maximum possible answer can be order of maximum between n and m. So the complexity of possibility check with the binary search will be order of n into m into log of maximum between n and m. The overall memory complexity will be order of n into m. The full problem analysis is available on the dashboard. Check this out. This concludes the problem walkthrough for our coding practice with Kickstart session for today. We hope you had as much fun as we did. Let us know in the comments, and Lizzie is going to close us out.
That's it for problem walkthroughs today. Thank you for your great engagement and participation. If you have any remaining questions, be sure to ask your peers in our Facebook group, where you can connect with the community and receive latest updates about Kickstart. In addition to this video, be sure to check out our full analysis on the dashboard, which you can find by clicking on the View Dashboard button at the top right of this page. When you get to the dashboard, select whichever problem you'd like to review, and then click on the Analysis tab. You will also be able to download the input and output files at the bottom of the page. Finally, be sure to check out our schedule page at g.co/kickstart and apply what you've just learned in our upcoming rounds and future practice sessions. Each round starts fresh, so you can participate in as many rounds as you're able to. The more you practice, the more you'll improve, so why not give it a try? And that's it. Thank you again for taking part in coding practice with Kickstart. Hope to see you in future rounds. We hope you had fun. Until next time, bye!